Dear delegates and invitees and my dear friends, today we have parallel technical session number 6. It is my great pleasure to announce that in this parallel technical session 6, we have Chair Professor H.N. Vasan sir from I.I.T. Roorkee and co-chair Dr. Shreyas V from GEM Foundation. And it is my pleasure to introduce the chair and co-chair. On behalf of the organizing committee, I'm extremely happy that Professor H.R. Vasan was former emeritus fellow and ex-professor and head Department of Earthquake Engineering, I.I.T. Roorkee, and former president of Indian Society of Earthquake Technology. He has teaching experience of 40 years and research and professional experience for over 45 years. He has successfully guided 6 PhD scholars and 26 MTech dissertation theses, and has published more than 85 research papers in reputed international journals and conferences. He has written 1 book and 2 book chapters. He has been awarded Life Fellowship of Indian Society of Earthquake Technology and a life membership of Indian Geotechnical Society and IGC specialization. His specializations include engineering seismology, seismic hazard and seismic assessment, risk assessment, seismic networks, regression relations, and pattern recognitions. He had the honor of being founder organizing chairman JM 2004 for all IITs and chairman JM 2005 for IIT Roorkee. Sir, I take this opportunity to welcome on this occasion and thank you for accepting our invitation to chair this afternoon session. I welcome you, sir, for this session. I would like to introduce our co-chair to the delegates, Dr. Shreyas V. Dr. Shreyas V has bachelor's degree in civil engineering and further specialized in the area of structural engineering. She defended her thesis in 2019 and obtained PhD from NITK Suratgal. Her PhD dissertation was on probabilistic seismic hazard assessment and site characterization of Southwest India. She continued her research career as a postdoctoral scholar at IIT Gandhinagar. Currently, she works as a seismic hazard modeler in GM Foundation located in Pavia, Italy. She has authored numerous journal articles and conference papers. She has delivered lectures on FDFIS, conference, and other ISET-funded programs. Her area of interest includes structural and soil dynamics, earthquake engineering, and seismology. So with this brief introduction, I welcome the co-chair, Dr. Shreyas V, to conduct this session, madam.
Thank you.
Sir, I request the co-chair as well as chair to, I will hand over the session to conduct the session.
Okay. Thank you, Dr. Govinda Raju, for the nice introduction and giving details of this session. So, on behalf of 7ICRAGEE, it gives me pleasure to welcome you all to this session, technical session 6. It gives me pleasure to have a special welcome to Professor Sebastiano who is the SOAP speaker for this session, and to other speakers and authors of the 6 technical presentations which are listed for this session. And also, I welcome all the attendees who have joined this session or who are likely to join this technical session for their interest in this topic. So before we begin, it is my honored duty to give a brief biodata of our SOAP speaker, Professor Sebastiano. for the benefit of the young researchers. Professor S40 is a professor in geotechnical engineering and vice rector for education at Politecnico di Torino, where he also received his PhD degree. He has been chair for the civil engineering program from 2015 to 2018. He is a member of the technical committee TC203 earthquakes and a past core member of TC102 in situ tests. These committees are of ISS MGE. He is part of the project team for drafting the new version of Eurocode 7, Geotechnical Design, Part 2, Ground Investigation and Testing. His research activity is mainly devoted to geophysical methods for geotechnical characterization, with particular reference to surface wave testing, seismic waves in porous media, and the use of geophysical techniques in the lab. His other research interests include seismic site response, soil structure interaction, structural dynamic tests for the assessment of existing foundation systems. He has published over 180 papers in scientific journals and technical conferences, 3 books and 6 books chapters. He served in the editorial board of Soil and Foundation from 2015 to 2017. He was awarded the Geotechnical Research Medal, Bishop Medal 2003 by the Institution of Civil Engineers, United Kingdom for the best paper on geotechnical engineering, and an honorable mention in the best paper category in the Geophysical Journal in 2011 by the Society of Exploration Geophysics, USA. With this brief introduction, I now invite Professor S40 to deliver his SOAP talk. And the title of his talk is Uncertainties in Small Strain Damping Ratio Evaluation and Their Influence on Seismic Ground Response Analysis. So, Professor 40, please, now you take the floor.
Thank you, Mr. Chairman, and good morning, everybody. First of all, I would like to thank the organizing committee of the conference to invite me to deliver this lecture. Obviously, I would have been very glad to visit India, as I have a very good. I remember very well the last conference I was there with you in India, and it was a really positive scientific and human experience, but for this time we are going to deliver online. So the topic has been presented by the chairman. Let's see a brief, let's start with a brief outline of the topics. So I will briefly introduce the different uncertainties that we have in ground response analysis. And specifically, then I will focus on the small strain damping ratio estimate, considering both the laboratory-based estimates and the back analysis of the in-situ measurements in downhole arrays. Then some hints from a case study, and finally, some discussion of approaches that we can use to estimate directly on site the small strain damping ratio from geophysical tests. So let's start with a brief overview of the site of the uncertainty in seismic site response analysis. They are indeed a key aspect in seismic hazard assessment. However, we have several uncertainties, both on the side of modeling and on the side of determining the site parameters that have an influence on the site response itself. Therefore, it is of foremost important to have a way to handling these uncertainties, and this can be set up in a very consistent procedure. If we clearly identify the uncertainties, we manage to quantify them and to manage their influence on the final results. I will show you some results having this in mind. So a brief overview of the different uncertainties that we have, they are reported in this slide. Basically, we have uncertainties related to modeling. So the choice of the nonlinear approach that we can use for modeling, that can typically it is either an equivalent linear approach or a fully nonlinear approach. And this has a major influence as all the input parameters that we have to consider, that are the shear wave velocity profile, the modulus reduction and damping curves that describe soil nonlinearity, and the input motion that we use in the analysis, and finally two other parameters that sometimes they are overlooked, but they are also of most important. The shear strength of the material, that is especially important where we are dealing with deep and soft deposit, in which we, during the analysis, we may develop failure at a certain depth. And finally, the small strain damping ratio. We will see that this is last but not least during the presentation. As we are going to see, there is an important influence from this parameter too. Just in order to provide a few hints, I will say a few words about the shear wave velocity profile, and then I will leave all the other uncertainty except the small strain damping ratio. So I will describe in terms of uncertainty the shear wave velocity profile, and in this respect we can clarify that especially the role of this parameter, that is maybe the foremost important parameter. Indeed, it is the one that actually governs the wave propagation in the elastic medium itself. Typically, this parameter is estimated with in situ geophysical test. That is the best way to directly evaluate these parameters. We have a certain uncertainty. We can model uncertainty with several different approaches. The most common are the Toro model, that basically is a randomization procedure, and the APRI recommendation that basically are based on a lower and upper bound approach. And finally, there is a new geostatistical model that we recently proposed in 2020. And I will spend a few words about this model, as this is a new opportunity to model this uncertainty. Also, as the Toro model, also the model proposed by Passeri et al. Is a model for randomization, but it has some important differences. First of all, there is a clear separation of the uncertainty that we have on the two basic parameters that are space and time whenever we measure velocity. And these avoid to have parasitic uncertainties. So this means that we are able to generate realistic, always generate realistic models, and these realistic models are always in agreement with some specific site signatures, as for example the Rayleigh wave dispersion curve, rather than the experimental transfer function and so on. The model has been calibrated on a large database of surface wave tests, but it is very flexible. It can be adapted also to other kind of geophysical tests. And typically, the most important aspect is that it overcomes some important drawbacks in the fact that of previous approaches, in the fact that it always generates, as I said before, profiles that are online, that are compatible with experimental site signatures without overestimating the actual uncertainty that we have at the site. I will skip the description of the other uncertainties that we have. You can find the full description in the paper and also in my invited lecture at the ISET conference in 2019, and I will now focus on the main aspect of the today's talk, that is the small strain damping ratio. So small strain damping ratio is typically estimated as a part of the characterization of the material in the lab. So when we characterize the material in terms of the nonlinear behavior of the material, we typically characterize the modulus reduction curve and also the damping curve that describes the variation of damping with strain, and specifically also the small strain damping ratio. Alternatively, we can use empirical relationship that are in any case still based on laboratory tests. I will not describe in details the laboratory tests that are very well known in the scientific community, but I will just stress a few points of importance that introduce uncertainties in the specifically in the evaluation of the small strain damping ratio. So let's start from the dynamic test. So typically the resonant column, in which a sample is excited at different frequencies, and basically exploring the response of the sample at different frequency, we can derive its resonant frequency. And if we consider the theory of elastic wave propagation from this frequency response curve, that is the response of the sample at different, when excited at different frequency, we can also derive the damping ratio considering the aperture of this frequency response. Main problem with the resonant column estimate is that the soil is assumed to be linear viscoelastic, so the method is reliable only in the small strain range, but this is fine for us, as today we are talking about the small strain damping ratio. But the main problem with the small strain damping ratio is that typically there is an overestimate that is due to the equipment generated damping. So internally to the equipment, we have some level of energy dissipation. This is typically overimposed on top of the actual real estimation of the damping ratio of the material itself. So for example, here you can see in a study by Meng and Rix the quantification of the estimation due to this effect. So which are the possible alternatives? One alternative is to consider the free decay that we have after we excite the sample itself. So after leaving the sample in after stopping the excitation system, we will have a free decay of the vibration. In this way, we can study the free decay and avoid to have an influence from equipment generated damping. Other possible to estimate small strain damping ratio in the lab is cyclic test, so basically torsional shear test or the direct simple shear test, cyclic obviously. And in this case, we really study the response to cycle of excitation, and then by considering a cycle of unloading and reloading, we can estimate the dissipated energy. From this, we can derive the small strain damping ratio. Main problem in this case is due to uncertainties in the definition of the hysteresis loop, especially when we are at very small strain. So it's the objective of today's talk. Indeed, this at small strain, the hysteresis loop is not really well defined. As you can see, this causes a given variability of the estimate of the damping ratio if we consider different cycles of unloading and reloading. And finally, if we deal with the laboratory test, it is important to take into account the frequency dependence of the small strain damping ratio. Indeed, several studies have shown that whenever we estimate the small strain damping ratio with a resonant column, we have an estimate that is larger than the one that we obtain in cyclic test. This difference is basically related to the different frequency of excitation of the samples. Indeed, that high frequency, as those that are explored with the resonant column, we have different dynamic effect, and this leads to a overestimation of the damping ratio. So if we want to compare the two estimates, we have to correct for this frequency effect. For example, on this picture on the right-hand side, you see data after they are corrected for the frequency effect, and you see actually that indeed now there is a very good agreement between the resonant column and the torsional shear. So this is what is concerned laboratory tests that are typically used to estimate the small strain damping ratio. But now, if we go and see what actually happened on site, we can try to understand if the values that we obtain in the laboratory are actually always representative of the damping ratio that we can expect. So now if we consider the back analysis of down-roll arrays, this is, if you wish, the most straightforward way to measure directly on site the damping ratio. Basically, what we do is we study the propagation of elastic wave on site, considering receivers at different depths. And from this set of data, we applying different possible approach, like the seismic waveform inversion rather than inversion based on the definition of the K0 parameters, or fitting the site amplification parameters, we can derive the small strain damping ratio. There are several application of this approach in the literature. In principle, this is relatively straightforward, as I said before. We start with a given estimate of the shear wave velocity profile and then an estimate of the damping, small strain damping ratio from laboratory test or from empirical relationship, and then we adjust the damping ratio profile in order to get a good fit with the empirical transfer function of the or a similar response parameters directly estimated on site on the basis of the down-roll array data. In principle, this is straightforward, as I said, but in reality, there is a very large sensitivity to the amplification parameter that I actually use. For example, these are a few case histories reported by Tao and Raj in 2019. As you see, for different case histories, we always have that the small strain damping ratio that can be estimated is much larger than the value that typically we estimate in the lab. And another important aspect to observe is that the value that we get in terms of damping ratio is different depending on the fact that we consider the transfer function or the amplification function or an amplification in terms of peak ground acceleration and so on. So this means that there is a variability in the estimate. This is an important aspect. The second important aspect is that there is consistently an evidence of the fact that the damping ratio on site is much larger than one that we estimate in the lab. Main problem with the use of the back analysis of down-roll arrays is that we need instrumented site, and obviously this is not always the case because we need to have instrumented site and we need to wait some time to record some meaningful events. The evidence in literature is in any case that the small strain damping ratio that we can estimate at the site is typically much larger than the one that we estimate in the lab, from up to 6 times the one that we estimate in the lab. The reason, is mainly due to wave scattering effect, especially when we have a complex stratigraphy, and to the fact that obviously our approximation of the 1D propagation, is an oversimplification in most of the cases. So possible strategies are a direct modeling of scattering and 3D condition, but this is obviously very time-consuming and very costly. We can consider an indirect model of scattering in 1D simulation, but in this, from this point of view, we need in some way to take into account the uncertainty that we have in the small strain damping ratio. So how to take this into account? There is an absence of a fully accepted procedure. In the remaining part of the lecture, we will make reference to the relationship proposed by the approach proposed by Stewart et al. That basically said we add on top of the estimate of the small strain damping ratio in the lab, we add an additional amount of damping that represent wave scattering. This additional damping can range from 0 to 5%. So we run a parametric analysis to take this variability into account. So let's see how this applies for a specific case study. So the example is taken from microzonation in Italy. If you want fully details of this, this is reported in our invited lecture in Reykjavik 2019. Rocca Fluvione site basically is as a profile in which we have some silty sands and then some silty gravel. And if we consider the results obtained with surface wave analysis with the MSW test, we see that at about 42 meters there is an interface with the bedrock below. So this is the shear wave velocity profile that we used as a reference. So again, in the paper in 2019, we explored the variability and the influence of uncertainties that we have in the shear wave velocity profile. As I said before, these uncertainties can be taken into account with the model proposed by Passer et al. In 2020. We took into account the uncertainties in modulus reduction and damping curves to take into account a nonlinear effect, and we used the curve that were developed by Ciancimino et al. In 2019. And considering all these uncertainties, we ran several ground response analysis in order to estimate the variability that we can have in the results. Variability is represented here in terms of amplification function. So we have the median estimate of the amplification function, and we are able to quantify in some way the associated uncertainty, the associated variability. As I said before, we have to identify uncertainties, we have to quantify uncertainties, and this is done with this randomization process, and we have to manage the uncertainties in order to see which are the influence on the final results, in this case the amplification function. Now, if we want to take into account also the role of the uncertainty on the small strain ratio, and if we follow the approach proposed by Stewart et al. In 2014, basically what we can do is to repeat the simulation here for the average shear wave velocity profile by considering just the small strain ratio that we have obtained for the lab, or increasing it either by 2.5% or to 5%. And now if we run the deterministic ground response analysis with these three hypotheses, what we get is something like this. So this is the influence that we can expect from our inability to estimate the actual value of the damping ratio on site. So this in blue is the estimate of the amplification function that we would have with the laboratory value of the small strain damping ratio. And obviously, when we add some additional damping to consider wave scattering, we will get lower result. Now it is interesting. So basically, this is the variability that we can expect due to uncertainties in the small strain ratio. Now it is interesting to compare this variability to the variability that, as I said before, we observed considering randomization of the shear wave velocity profile and randomization of the modulus reduction and damping curve. And this was the variability that we observed that was showed in the previous slide. So as you see, the variability associated to damping ratio can be even more important, or is in this example, is more important than the variability that we have from shear wave velocity profile and from the modulus reduction and damping curve. So if we do not account for a proper estimate of the small strain damping ratio, we may seriously overestimate the response at the site. So for this reason, it is important to have methods to estimate directly on site the small strain damping ratio. This can be done with a geophysical test. actually, this is something that is more on the research side, but we have to push in order to bring this to the state of the practice, because as we said, we have seen before, it is of foremost important to have a good estimate of the small strain damping ratio. So we have some promising method in geophysical test. I will briefly explore some of them. So considering boreal test, so either downhole or seismic CPT or cross-hole test, there are a few methods that were proposed in the past. I will just, for example, propose the method that was proposed by Lai Otzbecher in 2015, that basically is based on the spectral analysis of the wave that propagates whenever we run a cross-hole test with two receivers. So if we compare the signals at the first and second receiver, we can do a spectral analysis of this signal and basically observe that both the shear wave velocity and the damping are a function of the frequency, and considering the theory of of the linear viscoelasticity, and considering the Kramer-Kronig relationship, we can derive the small strain damping ratio as a function of frequency by fitting this expression. Other possible approaches are based on surface wave tests. Surface wave tests are becoming more and more used in seismic site characterization. This is related to the fact that they are quick and cost effective. The problem is that the interpretation is not so straightforward, but in order to provide you a reference, I put it over here the guidelines that we recently developed and are published as open access in the Bulletin of Earthquake Engineering 2018, and just to have the general description of surface wave test and some guidance for good practice. The surface wave test can be also used to estimate the damping ratio. Indeed, if we analyze the attenuation of the surface wave, we can get some useful information in order to derive the small strain damping ratio. Over time, several different methods have been proposed to estimate the attenuation of Rayleigh waves as a function of frequency. Here you can find a list of some of the methods that have been proposed. Specifically, now I will speak of the transfer function method, of the wave decomposition method that are very promising, and finally, one new method that we are actually developing at Politecnico di Torino. So, which is the basic concept, is that if we excite the soil with an active source, and then we record along a straight line the propagation of Rayleigh waves, we can estimate, we can study not only the dispersion, so not only the variation with the frequency of the phase velocity, but also the variation frequency of the amplitude. For example, in the transfer function method that was proposed by Rix et al. In 2001, basically what we do is that we consider the theoretical expression of the transfer function, we consider experimental data collected directly in terms of the variation of the transfer function as a function of frequency. And from this, we can, with a regression of the experimental data, we can obtain directly both the shear wave velocity profile and the attenuation of the Rayleigh wave dispersion and the attenuation of Rayleigh waves with a fully coupled process. So the advantage of this is that it's a fully coupled process. The advantage is that the cons is that it is reliable only with a single dominant mode. And then the procedure has been extended by myself in 2003, where using the concept of deconvolution, basically it is possible to use the same approach even when the source is not monitored. Another promising method has been recently proposed by Bergamo et al. This is the wave field decomposition method. The advantage of this method, again, also in this case, we have a decomposition of the full wave field, and again, considering a likelihood function, we can estimate the attenuation. The advantage is this method can handle multiple modes, so complex stratigraphy in which we have multiple modes of Rayleigh wave propagation. The problem is mainly related to the fact that it is a bit complex in terms of implementation. And finally, we recently have been working on a new approach that is based on the attenuation of the frequency wave number spectrum that can be obtained with a frequency domain beamformer approach. And this method has the advantage that has a very low computational effort and can obtain very good quality result. The problem is that in principle it is limited to a single dominant mode, but if we adopt it in conjunction with modal filtering, we can estimate the attenuation curve also for higher mode, not only for the fundamental mode. Just to provide briefly you an example of the results that we can obtain, these are data that have been collected with cooperation with Professor Brady Cox of the Utah State University, that formerly was at the University of Texas Austin, and our data related to the characterization of the site of the Garner Valley downhole array. And from these experimental data that were collected both with a large electromechanical shaker and also with a sledgehammer in order to have a comparison, this is an example of how it is possible to extract very neat, very clean, not only dispersion curves of Rayleigh waves, but also attenuation curve of Rayleigh waves. And so, considering this set of experimental data, so considering dispersion and attenuation of Rayleigh waves, then we can solve an inverse problem aimed at estimating not only the shear wave velocity profile, but also the damping ratio profile. A very important aspect on this is that not only we estimated the best fitting profile, but we have also an estimate of the uncertainty associated to the best fitting profile. And we can use this quantification of the uncertainty in order to manage the uncertainty itself. So some final remarks. Identification, quantification, and management of uncertainty is of foremost importance for any engineering application, but specifically for dynamic nonlinear problems like the one that we face in seismic design, because an a priori choice of conservative values is not possible. We know that for static problems, we can have a priori choice of conservative values, not for dynamic problems. So we have to manage the uncertainties that we have. Specifically, the effect of uncertainty in the small strain damping of the ground is as relevant as the uncertainty that we have in determination of the shear wave velocity profile and the uncertainty that we have in modulus reduction and damping curves. We have seen this in one example. And typically, approaches for estimating the small strain damping ratio rely on laboratory tests, but we have some underestimation because we do not account for scattering mechanism that we have on site. On the other side, using downhole arrays is very cost and time consuming, and promising approaches for the estimate of the small strain damping ratio comes from geophysical methods and specifically from surface wave test, because we can obtain reliable estimation, and also especially we can also evaluate the associated uncertainties, considering the uncertainties in the solution of the inverse problem. With this, I thank you for your attention, and I take the occasion to thank my two co-authors that are Mauro Aimar and Andrea Ciancimino. Both of them are PhD students at Politecnico di Torino, and I owe to them the preparation of both. I mean, a big help in the preparation of both the paper and this presentation. So thank you again, and I leave the floor for possible question and answer.
Thank you, Professor Forti, for a very interesting and informative lecture on a very important problem of uncertainties. And it has been demonstrated by you through lab and in-situ tests and the lab tests that consideration of effects of uncertainties is very, very relevant, and it should not be ignored. They have to be considered. So thank you very much for a very, very interesting and educative presentations. Maybe that we can take the question answer session at the end of all the presentations. And I hope you will be available till the end of the session. And